So yesterday we studied gravitational potential energy and kinetic energy. Remember that gravitational potential energy is one of many types of potential energy. There's another type called elastic or spring potential energy that we're going to get to today. There's also chemical potential energy. For physics 30, there are electrical potential energy. We can talk about magnetic potential energy as well, nuclear potential energy, which is a really weird beast to think about, but the one that we're focusing on so far is gravitational potential energy. Kinetic energy, however, refers to energy of motion. So, I can talk about the fact that a stick of dynamite has chemical potential energy, or I can talk about the fact that an object held above the floor has gravitational potential energy. But if I throw both of those objects through the air, they have kinetic energy. The stick of dynamite would also have chemical potential energy, and if I threw the object that's above the floor through the air so it's still above the floor, then it would also have gravitational potential energy. So what I'm getting at is sometimes objects have a combination of a potential energy and a kinetic energy, and we're going to have to grapple with that sooner or later. Yesterday, we went into more detail about where these formulas come from, not so much with the kinetic, but we approached things in terms of principles from previous units like applying force and acceleration and those types of things. But in the end, I would say you have to be able to calculate any of the variables in any of these two equations. Does anybody have any questions you would like me to go over? Yeah. Number 3 on part A. Okay. So the bob of a pendulum has a mass of 2 kilograms. The bob is pulled sideways so that it is 0.75 meters above the tabletop. What is the potential energy of the bob with respect to the equilibrium position? The phrase equilibrium position is going to be one that we use quite a lot in this unit and the next unit. It refers to where things would be if there was no energy in them. So, for example, and I guess I can get this thing going right now, if I take a spring and I hang a spring get it on there. What just happened there? There we go. And I take a spring, and there's a lot of different types of equilibrium positions, but if I take a mass and I put it on the spring and I set it oscillating, which is not something we're going to really concern ourselves with today, there's a lot happening here. The mass on the spring is going up and down. But if I were to let it settle down, this is the equilibrium position. Okay. On the other hand, I can talk about a spring, and I know that this question is about a pendulum, but I can talk about a spring with no mass on it, and I can say that the end of this spring has an equilibrium position right here. And an equilibrium position is something that we measure everything relative to. So if this is the equilibrium position, and I'm just going to say that that is at the tip of my nose if I'm hunched over a little bit, and I hang this on and let it come to rest, then if we talk about the displacement of this mass, it's the distance from here to the equilibrium position. So equilibrium position can take on a number of different meanings. And we're going to revisit this phrase in the next unit. However, when we talk about potential energy of the bob is the mass that's swinging around relative to the equilibrium position. What that means is the bottom of the bob is here at the equilibrium position. The bottom of the bob is here at that highest point or at that point. When I say what is the gravitational potential energy, that means I have to use that height, how far above the equilibrium position it is. If I said to you, what is the potential energy of the bob relative to the tabletop, you would use 0.75 meters as the height. So relative to the equilibrium position means that this is what we're going to use for the height when we calculate mgh. Does that make sense, Sahara? Okay. Essentially what we can do is, and I realize these distances now looking at the diagram are measured to the middle of the bob, but I hope, just give me a second to lock something in here. I hope that you can appreciate that this height is the same as the distance from the center to the center. So whether I measure center to center or bottom to bottom, it doesn't matter. I still am going to take that 0.75 minus the 0.5. And that's going to give me for a height .25 meters. So I can put in the mass. What was the mass of Bob, or the Bob? 2 kilograms multiplied by 9.81 newtons per kilogram, multiplied by that 0.25 meters. You'll notice I'm starting to put units in more often now than I did before, and my reasoning is by this point in time the unit should not be a confusion to you in solving this equation. So we're going to multiply this out. And get approximately 5. Right? Well, 4.9. I can see the answer there. So the gravitational potential energy relative to the lowest point is 4.9 joules. The reason why we use the lowest point, the equilibrium position, is that's as far as it goes. So if I release it, it's going to lose 4.9 joules of energy to get to that bottom point, which means it will have 4.9 joules of kinetic energy at that lowest point. Have I answered your question? Okay. Other questions? Let's just stick with assignment A first. All right, what about B? Zahara? 6? So what is the kinetic energy of an object when an average net force of 8.7 newtons accelerates it uniformly from rest for 0.12 seconds? So for number 6, if you want to find the kinetic energy, you have to use 1/2 mv squared. I mean, there's a different way to do it, which I may show you in a second, but this is what we're going to have to do if you want to just stick to the script and use the formula. So what do we know? We know the mass, but we don't know the speed that it's going to reach to give it that kinetic energy. What's happening here, we're reading a little bit into this equation, or this question rather, is that the initial speed is 0. It accelerates from rest. It's going to reach some final speed, and this is the speed that we want to know to find its kinetic energy that it's going to have. And this is beginning to look a lot like a kinematics dynamics situation, because you're told the net force. The fact that it says average, you know, we really haven't talked about this. But when I look at Newton's second law, where I write F equals ma, and I'm going to leave the vectors out of it, I've really impressed on you the fact that it's not F equals ma, it's F net equals ma. What I haven't explained to you, and it's going to become more important in the next unit, not in this unit, but we might as well talk about it now, is it must be the average force. Because when I apply a force to an object, let's just say I have a car that's in neutral, it won't start, and I just want to push it off to the side of the road. And I start pushing on it, the amount of force I apply to begin with is probably quite large. And in fact, it's actually very small to begin with because I'm just touching it, barely pushing. And then in a short period of time, that force climbs to a very big force. But once the car gets rolling, due to its inertia, I don't have to apply as great of a force. You know, that force to begin with needs to be really large to overcome that static force of friction. So when I determine the acceleration of the car, I have to use an average. So this is average. Now, if I want to find VF, and by the way, I also know the time is 0.12 seconds, kinematically speaking, this stuff to the right of this squiggly line is not enough to find the acceleration, or not enough to find the final speed, rather. I need one more thing, which will be the acceleration, and I can find that by taking the magnitude of the net average force divided by the mass. So what's going to happen here is we're going to have to calculate the acceleration first. Then we will have to calculate second the speed reached, and then the third thing we'll be able to do is find the kinetic energy. So let's run some numbers through our calculator. I'm not going to bother writing down some of these numbers. It's 8.7 newtons and it's 5 kilograms. So we should all be fine with using F equals ma, where F is 8.7 newtons and m is 5 kilograms. To find the acceleration, you would take the net force divided by the mass, 1.74 meters per second squared. So the acceleration is 1.74 meters per second squared. We can put that into this list of kinematics descriptors and then go on a little treasure hunt for a formula that we could use to find VF. The formula will be acceleration equals VF minus VI over T. Once again, that's not the formula that appears on your formula sheet. On your formula sheet, I think it says acceleration equals delta V over delta T, but using a little bit of common sense, this is what it becomes. Since VI is 0, this formula now becomes acceleration equals VF over T. And again, knowing VI and T should be like stealing candy from a baby to find the final speed. Just multiply them. You can see that in the equation. So if I multiply the acceleration by the time, I get a final speed of 0.2088 meters per second. And then, of course, I have to go over here and use my kinetic energy formula. Kinetic energy is 1/2 times the mass, which is 5 kilograms, times that 0.2. I'm just writing 0.2 meters per second because I don't have a lot of room. 0.2088 meters per second quantity squared. So 0.5, that's my 1/2 times 5, and then times my answer, which I need to square. So I get about 0.11 joules, which is the answer. Any other questions? Number 2? So number 2 says the kinetic energy of a 20 Newton object is 500 joules. This, when you see something like a 20 Newton object, you're being told the weight of the object. This is the weight. And it's not the best way to describe an object because, I'm being maybe a little facetious here, but I don't know, is it 20 newtons on Earth? Is it 20 newtons on Mars? That number depends on the location. We assume, of course, it's on Earth. So I've talked about this before, but I want to talk about it again because it might have been a while. When I say a .0 Newton kitten, I'm talking about the weight of the kitten. Can somebody explain to me why I know that in a very round way it's a 0.3 kilogram kitten? I'm being very flexible with numbers here. Alex?
Kilograms by 9.81, which is roughly 10.
Right. So your formula in relating weight is the force due to gravity. Your formula is weight equals m times the gravitational field strength of 9.81 newtons per kilogram. It's not an acceleration, it's a gravitational field strength. And 9.81 is pretty close to 10. So I'm just using this as an analogy. If you said, somebody says, oh, how much did that kitten weigh when it was born? They probably want to know how many grams or kilograms it is, but you being a physics person would go, oh, okay. Its weight is 3 newtons. And they would look at you funny and you would go, oh, okay. That's 300 grams or 0.3 kilograms. The point is we should be able to convert back and forth between mass and newtons in terms of mass and kilogram and weight using this formula. And the reason why that's important is in question 2, we have the kinetic energy and we're asked to find the speed. Well, we can put the kinetic energy here. We can put the mass in, which will be 20 newtons over 9.81 newtons per kilogram. You most likely would do that calculation elsewhere, like just off on the side. You understand why I'm taking 20 newtons divided by 9.81? And that's the mass. It's going to be very close to 2 kilograms. And then we'll have v squared. I regret writing down 20 over 9.81. I really think it's best that you calculate that elsewhere. So we would go 20 divided by 9.81. It's 2.038 kilograms. So how do I get V by itself? I have to take that 500 joules and multiply by 2 because I'm dividing by 2 on the other side. And then I have to divide by the mass, and then I have to take the square root of the answer. So it's about 22.1 meters per second. Is that okay? Okay. Any other questions? Okay, before we move on, it's at this point that I want to explain something, and it's come up a couple of times over the past few classes. And I've said, I'm not going to worry about explaining this to you now. When the time is right, I'm going to explain to you. And the time is right. And we started off with this formula for work. And in terms of units, work is measured in joules, force is measured in newtons, and displacement or distance is measured in meters. And what I said at the time is, let's not worry about why, but when you multiply newtons times meters, you get joules. Okay? And then we could do the same kind of thing with the kinetic energy and the potential energy formulas, but I don't want to go there just yet. Why is it we get that? Okay, well, I'm going to back up, and this I have explained to you before. Net force equals mass times acceleration. And mass is measured in kilograms, and acceleration is measured in meters per second squared. So if I said to you, what is the unit of force? You could say it's kilograms times meters per second squared. And the story as I tell it is, so I'm going to write 1 Newton equals that. The story as I tell it is that, Isaac Newton comes up with this F net equals ma idea. People use it. They predict what happens in the real world, and their observations match their predictions. The formula works good. But sooner or later, somebody says, do we have to keep writing kilogram meter per second squared for the unit of force? And somebody else comes up with the brilliant idea of saying, well, why don't we just abbreviate that? Why don't we condense that? And for that reason, these are called fundamental units. But this is called a derived unit. And what a fundamental unit is somebody somewhere along the way, it's hard to imagine this, when science was being constructed in the world and we had to measure things, somebody said, well, let's measure something to be a meter. And they defined a meter to be a particular length. I can't remember, so don't quote me on this, but I think the original definition of a meter was how far along the surface of the Earth you go for a particular angle of latitude. Something like that. Very weird definition. But then sooner or later, and I believe I've told you this, somebody took a piece of metal made out of iridium and they put two little scratches in it and they said, that's a meter. And this thing still exists in a museum somewhere in France. This piece of metal, and the length of it is defined as a meter. Somebody decided somewhere along the way that this is a kilogram of mass. Not this exact one. It'd be worth a lot of money if this was the original one. But somewhere, and it's also in a museum in France, there's a chunk of metal. I think it's also made of iridium. It's under a glass jar, so you can't touch it and put your fingerprints on it or add mass to it. And its mass is defined as 1 kilogram. A second was originally defined in a certain way. All of these units have more sophisticated definitions now, but they were defined. They're fundamental units. A derived unit is a combination of them. Okay? So now let's talk about work equals force times displacement. This is kind of a definition formula, but not really. Would you agree, just using the common sense notion of work, that force and displacement are the two things that determine how much work a person does? If you apply a greater force, you do more work. You provide more energy to a system. And if you apply that force over a larger distance, you do more work. So this formula is the definition of work, kind of. And people do some calculations. They take force, which is measured in newtons. Why is force measured in newtons? Because it's defined to be a newton. Kilogram meter per second squared. And we multiply by meters, so we start doing all these calculations. And again, this is just a story as I tell it. And people say, okay, well, how much work was done? 25 Newton meters. 73 Newton meters. And people get tired of saying Newton meters. And somebody puts up their hand and says, can we abbreviate that? And it's abbreviated as a joule. And if you stop and think about that, this you do need to know. This is a formula of quantities. This is a formula of units. It's different. But if you stop and think about that, 1 joule is a Newton meter, but that means 1 joule is a kilogram times a meter squared per second squared. Why is that? Well, because a Newton is a kilogram meter per second squared. And I'm going to take that Newton and multiply by a meter, so I get kilogram meter squared per second squared. The units of a Newton are the same as a kilogram meter per second squared, and the units of a joule are the same as a kilogram meter squared per second squared. Okay. So if you start looking now at the formulas that we learned or reviewed yesterday, what kind of units do you get when you take mass, which is kilograms, times g, which is newtons per kilogram, times a height, which is meters? Well, the kilograms cancel. You get newtons times meters. But a Newton is a kilogram meter per second squared times that other meter gives you a joule, because this combination of those fundamental units gives you a derived unit of a joule. If I use the formula on the right, kinetic energy is 1/2 mv squared. The units of mass are kilograms. The units of speed are meters per second, and I need to square that. So I get kilograms times meters squared per second squared, which is joules. You know, how important is it for you to know that a Newton is a kilogram meter per second squared and a joule is a kilogram meter squared per second squared? Pretty important in Physics 30. It shouldn't blow your mind when in your Physics 30 class they say, oh, right, and a joule is this combination of units. Any questions about that? What are the units of this? You'll notice I just kind of ignored that. What are the units of 1/2? Jay, do you know? Nothing. There's no units. It's what we call in science and math a pure number. It's just a number. Okay? It's not 1/2 of a pizza. It's not 1/2 of a grasshopper. It's just a half. It's just a number. It's a half of mv squared. Okay, now we're going to move on. I did want to get that out of the way, and today was a day that I feel it fit nicely. So we're going to look today on page 32 of your unit handout. This is the next lesson, which deals with something called Hooke's law and elastic potential energy. Elastic potential energy is energy that's stored due to the elastic nature of a system. So if I take a piece of foil and I crumple it up into a little ball and I bend it into a shape and I put it on around an elastic and I put the elastic between my fingers and I pull it back and I point it at something, there's energy stored in that system. Because if I let it go, it's going to have the ability to do work. Okay. There is energy stored. There's the equilibrium position of this mass. There is potential energy stored in the system right now. Because if I let this go, it does work. It moves. Okay. This is called elastic potential energy or spring potential energy as well. There's really not much of a difference between spring potential energy and elastic potential energy. I suppose the difference is we would probably prefer to use the word spring in the potential energy description if it's a spring, like you're seeing here. But if it's an actual piece of elastic, you might call it elastic. You can interchange those words. So let's start off with Hooke's law. Long time ago, 350 years ago approximately, Robert Hooke was an English physicist, and he demonstrated that the stretch produced by a force applied to a spring is proportional to the magnitude of the force. What does that mean? It means that the more you stretch, it means that the more you pull on it, the more it will stretch. If you want to stretch a spring twice as far, then you're going to have to apply twice the force. Now, for the time being, it's easiest to teach this to you by assuming that the force is a force of gravity produced by hanging a mass on the spring. So I could take this spring and I could say, well, let's apply a force this way, and it stretches a certain amount. Let's apply more force this way, and it stretches more. But it's difficult for me to measure this force. I would have to use a spring scale. On the other hand, if I want to apply a force of 5 newtons to this spring, this is a 500-gram. This is a 500-gram mass with a weight. This is good. We had this conversation. This is 500 grams, 0.5 kilograms. If I take 0.5 kilograms times 9.81 newtons per kilogram, this weight, it's not 5 newtons, it's 4.9 something newtons. But look how much it's stretched. What Hooke's law is saying, and again, I'll use my nose as the reference point for the equilibrium position. Okay? I'll use the top of my lip here. What Hooke's law says is if I measure how far this spring stretches from here to here, and then what I decide to do is instead of using a force of 5 newtons, I use a force of 10 newtons. and I measure how far it stretches from the equilibrium position to where it is now, it will be twice as great. That's what a proportionality means. It means this. And it might not be a bad idea for you to just sketch that. It doesn't have to be a big diagram because we're not going to add anything to it. Just do a little tiny sketch someplace here. This is what Hooke's law says. Now, normally in science, we say that you put the manipulated variable on the horizontal axis. And it's the force that we're manipulating here. So we're going against the grain of the system here. We're not doing what we should be doing. But that's what Hooke's law says. And by the way, it goes through the origin, because if this is the equilibrium position right here, what's the displacement of this point when there's no force on it? Well, nothing. It's only when I start applying a force that I get a displacement. So displacement does not refer to length of the spring. It refers to how much the spring has stretched. So if this spring is 6 centimeters, and then when I measure it here, it's 16 centimeters, then the displacement is 10. There's a relationship, and this is the relationship. Fs is the spring force. We're going to change this subtly in a few minutes, but Fs in this formula, which is on your formula sheet under dynamics, Fs is the force that the spring exerts on the mass. So I want to talk about this right now. I'm going to put this 500-gram mass back on the spring. And I hope you would agree that this force of gravity is towards the floor. Yes? So the force that I am applying to the spring is towards the floor. What direction is the force that the spring exerts on the mass? Up. Okay. We'll come back to that. But it's important for you to note that in my hanging spring example that we're looking at here, the force that the spring exerts on the mass is towards the ceiling. K is something called a spring constant. And I'm going to come back to that in a second. I'm not telling you too much about it. And x is the displacement. What I will tell you is that the spring constant tells us in some way how stretchy the spring is. So if I hang a, I'm going to need your eyes to help me out here. 100-gram mass. If I hang a 100-gram mass on this spring, it stretches about, I don't know, 3 centimeters. If I hang a 100-gram mass on this spring, it stretches a lot more. And by the way, the spring constant of this spring that you're looking at that's stretched right now is still the same. The spring constant is the same as long as it comes back to its original shape. If I take one of these and I stretch it so that I'm actually changing the length, see that? The spring constant now is different. If I were to put this mass on here now, the distance it stretches is probably going to be more. I mention this because tomorrow you're going to be doing a lab where you determine a spring constant. You have to make sure that you don't put such a large mass on it that it wrecks the spring. Do you understand by wrecks it? It stretches it and it deforms it so it doesn't come back to its original spiral. Metal slinkies are like this. If you had a slinky and you play with it too much, it ends up losing its shape and getting longer than it really is. So the spring constant is simply something that is telling you how stretchy or non-stretchy the spring is. I think I have a spring here. thought I had one. I do. I don't know what this is from. It's an automotive spring from something. It's very, very difficult to stretch this. By the way, you can talk about compressing it as well. I don't know what this is from. Does anybody recognize it? I mean, it's too small for any kind of strut or shock absorber or anything, but it's something to do with an engine. I'll have to ask Mr. Blacker because he's the one who gave it to me originally. So X is the displacement measured in meters, and F is the force that the spring exerts on the mass. There's your formula. Fs equals negative kx, and the force is a vector, and x is a vector. Okay, they're both vectors. We're going to come back to that formula in a little bit, but in the meantime, a couple of questions. How does the force applied to the spring change the amount that the spring stretches? All this is asking you to do is put into words this picture. And essentially, the force is directly proportional to the displacement. The displacement, that word displacement means how much the spring stretches. So if you stretch a spring twice as far, you have to apply twice the force. This direct proportionality assumes that you don't ruin the spring by stretching it too much. Okay. Perfect example are the hair elastics that I use. I bought some new ones yesterday because the ones I use, after a while, they don't have as much tightness to them. They get stretched out of proportion. Number 2, in the formula shown for Hooke's law, Fs is the force that the spring exerts on the mass. Why do we have a negative sign in the equation? Well, take a look at the equilibrium position of the bottom of this spring. And it's really convenient that we had that conversation at the beginning about equilibrium positions. So take a look at the location. You can use the bottom of my lip if you want. In what direction is the displacement? Towards the floor. In what direction is the spring pulling on the mass? Towards the ceiling. So these two vectors are in opposite directions. In other words, and I don't really know that I want you to write this down, but if x happened to be negative 10 centimeters, then Fs, the force that the spring exerts on the mass, would be negative k times the negative 10. Don't worry about the units of anything else yet, but you would end up getting a negative times a negative, which is a positive force, which makes sense. Because if the displacement is in the downward direction, the force on the mass has to be in the upward direction. And remember, it's not the force on the spring, it's the force on the mass causing the displacement. So the answer to this question is that when you have a spring that is stretched, the displacement is in one direction, but the force on the mass by the spring is in the opposite direction. Fs is opposite to the displacement. And that negative is there because somebody at Alberta Ed, and well, I shouldn't blame it on Alberta Ed. It's like this in textbooks too, even in university. Because when you include vectors, you need the negative. Now that being said, everyone, I never use the negative. I mean, if I were asked for the direction of a force, I would think about it and put in the appropriate direction. If I were asked for the direction of the displacement, I would put in the appropriate direction by thinking about which way things have been moved. So very often when I write Hooke's law, I write that, and in reality, I don't even think I'll ever really write that. Hooke's law. And you know what? To go even further, I would probably just do this. F equals kx. And I know that it's the force. Okay, so when I look at this state right now with this mass hanging in the spring at the front of the room, you know, if I said, what's the force? The force is the force of gravity. What's the force that the spring exerts? It's the same, but in the opposite direction. So when you talk about Hooke's law, that force is simply the force involved in the stretch. Okay. All right, warm-up number 1, an experiment, and this is going to be an experiment that you will do tomorrow. Very close to anyway. Somebody tests Hooke's law. Students suspend a series of masses on a spring, and they measure the displacement. Now, this chart has position in it, but since the position when no mass hanging on it is 0, these numbers are really the displacement. Somebody tell me how the students went from this column, which they measured, to this column, which they calculated. Alex?
Because grams, so like 200 is 0.2, and then you multiply that by 9.81.
Right. They've taken the mass in kilograms and they've used your weight formula, force due to gravity equals m times g, gravitational field strength. They've calculated that. So what we are asked to do is verify Hooke's law by plotting the force exerted as a function of the position on our calculator. So what we are asked to do is plot this graph on our graphing calculator. The force, and I'm not going to worry about vectors here. This is in newtons. It's really the force due to gravity as a function of x, which is in meters. Okay, how do we do that? I'm just curious, how many of you remember how to enter this data into your calculator? Where do we go in general? And how do I get in there? Okay, so I normally just go stat edit, and I'm going to be brutally honest with you. This is a little embarrassing. I never knew the word list was there. I've never seen that before. We want to go to our lists. That makes it so, well, I guess then we can go enter. No, we can't edit the lists there. We can access the lists there. That's too bad. We still have to go stat edit to see our lists where we are able to put in numbers. Does anybody remember which variable goes in L1? Is it X or Y? It's X. L1, L2, in order, goes 1 to 2. X comes before Y in the alphabet. So we're going to put in for X 0, 0.05, 0.099, 0.146, 0.197, 0.245, and for Y we're going to put the forces. I'll be honest with you here, I don't think it's ever really a good idea when you do an analysis, and I'll mention this tomorrow. I don't think it's a good idea to use 0 and 0 as a data point. I think that can skew your results, which means make your results inaccurate. Then what do we have? 1.96, 3.92, 5.87, 7.85, 9.81. Double check all of the numbers, and I think we're good. So how do we plot this graph now? Because we're asked to sketch what we see. The first thing to note is your graphing calculator graphs two types of things. It graphs functions which if you go y equals, you might have something in there from a different class. If you do, clear it out. Your graphing calculator also plots data. And if you want to plot a function, you go to y equals. If you want to plot data, you go second y to get to stat plot. And I have a number of plots on my calculator, at least 4, but they're all off right now. So I hit enter to access one. I hit enter to turn it on. If you have a TI-84 calculator or higher, then you're going to choose these options in a bit, but we won't worry too much about that. Are they still there? They're still there, okay. We want this for the type of plot. We want list 1 to be X, list 2 to be Y, and the mark we want is that. And what I would recommend here now is going to your window. So window button is right here, and manually setting up your axes. So my X goes from 0 to 0.245. So I'm going to go from 0 to 0.3. X scale simply tells you where it's going to put a tick on your graph. So if I put a 0.1, it's going to have a 0, and then 0.1, 0.2, 0.3. It's going to show ticks there. If you want it to go 0.05, then it's going to show a tick. If you want to go 0.05, then it's going to show a tick every 0.05. That's not important. For my Y, I'm going to go from 0 up to, my biggest Y is 9.81, so I'm going to go up to 10. Maybe with a tick every 2. I've entered my data. I've turned on my stat plot. I've set up my window settings, so I should see the data. I can't see the 0, 0, by the way, because it's right at the origin. Have we verified Hooke's law with this data? Yes, because Hooke's law says it's a straight line. So, what do we get? Well, you can sketch it if you want. I'm not going to waste my time doing it. You can repeat that sketch that we put at the top and put it down in the space there. Am I going too slow? Okay. What's the slope of the line? How do we find the slope of the line? Well, what we do, we've already established it's a straight line. You can see it, right? What we do is a linear regression. How many of you remember that? Did I show that to you in this class? I did. I can't remember where. I think it might have been back in kinematics when we were finding slopes of lines. You go stat, and then calculate, and you choose lin reg. Now, I'll warn you right now, I think, maybe not, my calculator might show some additional information here in a second. Maybe not, because I think I reset it. If you don't have a TI-83, when you hit enter, you have to hit enter, 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 or scroll down to confirm everything. Here, I just do this. I don't get what I thought I was going to get, which was something extra. But what I do get is an equation of the line that says y is equal to 40x minus 0.02. So this is a y equals mx plus b situation, but m is actually a on your calculator. So what is the slope of the line? Well, it's 40. But we were talking earlier about units. Things have units. You know, if you say how much, and I say 40, well, are you talking about $40? You're talking about $40,000? You're talking about 40 nickels? Things have units at times, and the units here, so your slope is 40. But since y was in newtons and x was in meters, and slope is rise over run, the rise would be a number of newtons, the run would be a number of meters. This is 40 newtons per meter. It's telling you that for every 1 meter you want to stretch that spring, you have to apply a force of 40 newtons. And in fact, since, don't worry about what I'm doing here, please. Since if I were to graph that equation, it goes through the data and it's a straight line through the origin, we already know that the equation is force equals the spring constant times x. 40 newtons per meter is the spring constant. It's what you multiply x by to get the force. Excuse me for a second. So when we go back to the top of the page there, and I just kind of left you hanging as to what the spring constant is, the spring constant is a number of newtons per meter. And a very large spring constant would be something where you have to pull quite hard to stretch it. But a very small spring constant would be something like this spring where very little force per newton, very little number of newtons per meter is required. All right, let's do a couple of quick questions with Hooke's law. Let's move on to elastic potential energy. So turn the page, please. Imagine an archer pulling an arrow back in a bow to a displacement of 20 centimeters. Well, the bow is a spring. A bow obeys Hooke's law because when you release the arrow, the bow goes back to its original shape. So what that means is if the bow follows Hooke's law, this is what the graph would look like, where this distance here is 0.2 meters. This is x. And this force up here is some force. Okay? And I want to stress something here. This force up top, I'm going to call it the maximum force. You need to understand that that force is not the force applied in pulling it back. It's not even an average force. It's the force required in holding the bow in that position. If you look at the force needed to hold it at 18 centimeters, it's less than that force. So this force, whatever it is at the top, is not an average force. It's the maximum force. Okay. Well, there's the sketch. The archer does work to the system. Would you agree that the archer applies a force over a displacement? Okay. The archer did work. The archer transferred energy. Where is the energy stored? Aoki. In the arrow. Good. I'm going to just say in the bow arrow system, because you could argue that it's stored in either. And when I let it go, if you think it's stored in the bow, it's going to transfer it immediately to the arrow. But maybe ask this question, or answer this question. What type of energy is in the bow arrow system? Right. So it's stored in the potential energy of the arrow, or the potential energy of the bow arrow system. I'm actually going to stick with arrow. So, stored in potential energy of the bow. Wait. Is that gravitational potential energy of the bow? No. That's not. The archer didn't pick the bow up and then is going to drop it. What kind of potential energy elastic. So stored in elastic potential energy, I'm going to change my mind and say of the bow. I don't want to say elastic potential energy of an arrow because an arrow isn't elastic in nature. It isn't springy. I could say spring potential energy. There's no difference. It's a springy system. Okay. Show how you would find the work done to the arrow using the graph. We talked about this yesterday. The work done is going to be the area. So how would we do that? Well, the area of a triangle is equal to 1/2 the base times the height. Well, 1/2 the base is how far it's been stretched. It's 0.2 meters. I'm not going to put in the number, though. I'm just going to do this in a general way. The base is how far this thing has been stretched. The height is the maximum force, which, as I said, this requires deep thought, is the force that the archer is exerting on the system at that point, which is the same as the force that the bow is pulling on the archer's fingers with, which is kx. It's Hooke's law. It's kx. So when you look up here at this mass stretching this spring, the force being applied here is the force being applied at this point. It's the maximum force. There is less force required here and less here. It's the maximum force. And that means that we get the area, or the work done, equals 1/2 x times kx, or the work done is 1/2 kx squared. And what we have just figured out is a way to calculate elastic potential energy. You take 1/2 times the spring constant times the displacement squared, it will give you the elastic potential energy stored in a system, because work done is change in energy. There's your formula. It's a new formula. If you look at your formula sheet, under momentum and energy, here's your gravitational potential energy, here's your kinetic energy. Now we have elastic or spring potential energy. We need to use standard units in this formula. Let's see about the units. The units of this would be newtons per meter, because that's what the units of K are, times the units of displacement squared, which would be meters squared. Meters squared over meters gives you meters. You're left with newtons times meters, which is a joule. All right, let's try a couple of questions now. A spring has, I don't know why I've got an spring. A spring has a constant of 4 newtons per centimeter, and it's stretched 6 centimeters. How much elastic potential energy is in the system? First of all, the displacement is 0.06 meters. We need to work in standard units. And the spring constant is 4 newtons per centimeter. How many newtons per meter would it be? This is a little tricky. Anybody want to stick their neck out on this one? Nate?
0.04.
No. And that's the mistake that people will make. You'll go, well, I'm converting centimeters to meters, so I divide by 100. You're not converting centimeters to meters, though. You're converting newtons per centimeter to newtons per meter. So think about it this way. If it requires 4 newtons to stretch it 1 centimeter, then it would require 100 times more newtons to stretch it 100 centimeters. So this is actually going to be 400 newtons per meter. So what's the elastic potential energy? At this point in time, this is child's play. It's 1/2 kx squared. I'm not even going to write down these numbers. 0.5 times 400 times 0.06. You might be surprised to learn that forgetting to square this is a very common error, like very common, more common than you would think. So I get 0.72 joules. Any questions with example 1? By the way, with example 1, instead of saying how much elastic potential energy is stored, I could have said how much work is done, because work is change in energy. The spring is stretched to a position of 35 centimeters from its equilibrium position. At that point, the force required is 10.5 newtons. What is the elastic potential energy stored in the system? Well, EP equals 1/2 kx squared. And I think it's pretty clear that x is 0.35. But what is k? Is this the final example?
Yeah.
Okay. What is k? Or how can we find k? Gia, what do you think? I see you doing something on your calculator. I think you know. No? Kai?
The opposite of force due to gravity.
We're talking here about K, though, which is not a force. K is how many newtons per meter it requires to stretch it. Alex, you got an idea?
Well, it takes 10.5 newtons to move it 0.35 meters. So would you use like a ratio to convert that to whatever it is over 1 meter? So like
Yes.
like 10.5 over 35 or reverse side.
Right. So what Alex is saying is, if we want to know how many newtons it is per meter, we could set up a ratio and go 10.5 newtons over 0.35 meters, and we could solve for x, right? But by the way, I just want to make sure here you understand x is not that number of newtons. It's newtons per meter. We don't even have to do that. Before I show you the quick way to do it, does anybody have any other ideas? Use Hooke's law. Put 10.5 newtons in. Put 0.35 meters in. And solve for k. Which is effectively what you would be doing, isn't it? So let's do that, and then we can finish the question. And I have one tiny little bit of a detail I want to add to this. So the spring constant is 30 newtons per meter, and then we work out what this is. .5 times 30 times 0.35 squared. About 1.8 joules. Any questions with that one? Okay, so before you get started on the practice, I've told you, and it's true, that the spring or elastic potential energy stored in the system is the work done. That's true. So what if a person looked at this question and said, well, this question is asking me to find the elastic potential energy, so I'm going to find the work done. We know the answer is 1.8 joules, correct? This other person says, well, but work is force times displacement, and the force is 10.5 newtons, and the displacement is 0.35 meters, and they work that out. Now, what do they get? Well, they get 3.675 joules, which is wrong. Why is it wrong? I'm going to put up this wrong solution on the right-hand board, on the right-hand screen. And I'm going to put the correct solution on the left-hand screen. What's wrong with the person's thinking on the right? Alex? Say that again. I didn't catch the first part. Right. That 10.5 newtons is not the applied force for the whole time. We made a big deal. Now I'm going to go back to this one. We made a big deal when we used this formula to say that this is a applied force that's an average, right? And I made a big deal with this question and any stretching of a spring and pointing out that force at the end is just the maximum force. If you want to use this formula, you have to divide this force by 2 to get an average force. And guess what's going to happen? You're going to get 1.8. I want you, though, to pay careful attention to the fact that, and then it's correct, I don't think doing it this way is best. Even if the question said how much work is done, I think it's better for you to say, okay, work is potential energy. I'm going to calculate the potential energy. So you can see a number of questions on the next page. I would say if you do the additional problems, that's more than enough practice. I don't think you need to do the text assignment. So get to work. You've got about 10 minutes left in class. Tomorrow we will be a little bit more relaxed. We're going to be doing a lab and going over any of these questions. And then we're going to move on. It's looking as though, if I had to pick a date for your unit exam, it's late next week, like maybe Friday. I have to talk with Ms. Jorgensen, though, and work that out. So get to work on those in the meantime, and I will be around to help you out when you need it.